Good evening, everyone. On behalf of the AEE Kolkata chapter and on behalf of Energy Management Department from ISWBM, I extend a warm welcome to all of you for attending today's webinar. On the onset, I would like to mention that our Kolkata chapter has been awarded the Best Community Service Award from AE USA this year. This award has been possible due to the numerous activities and various things that we do at our college to promote energy awareness and to make people aware of the adverse effects of uh, climate change and the related dangers associated with it. We conduct monthly webinars like this every month, and also we spread messages of energy awareness and climate literacy among the students, among the academicians of our city, and also among the global community. I am also proud to announce that 5 students from the current batch of energy management has been awarded the prestigious AE International Scholarships. These scholarships are sure to give them a boost when they will become energy professionals in the future. Now coming back to today's webinar. So the topic for today is the role of carbon storage in achieving net zero. And today we have with us our honorable speaker, Dr. Raj Banerjee, who is an advisor in Schlumberger USA and senior member of Association of Energy Engineers USA. Dr. Banerjee has a PhD degree in applied mathematics from Imperial College London, a master's degree in petroleum engineering from the University of Tulsa, and a bachelor's degree in petroleum engineering from IIT Dhanbad. He has numerous patents and publications. He is currently based in Houston, where he provides technical advice on petroleum engineering software and workflows. His areas of interest include subsurface modeling and simulation, petroleum production engineering, carbon storage, and machine learning. Thank you, sir, for kindly consenting to grace today's webinar. The stage is all yours now.
Okay, maybe some technical issue is there. Maybe I'm calling him. So in between, let
Yeah,
all of
hello.
you please
No,
go.
that
Yeah,
is
yeah. Okay,
is
okay, now
okay.
fine. Yes,
Yeah.
yes, yes.
So no, I'm trying to share my screen.
Okay.
And
Uh,
first, let me
yeah, switch on your video first. Yeah, sure.
let me first switch on my video.
Hmm,
And
hmm. Very good morning.
good morning, or good evening to all of you. Yeah, it's a different. Can you see me now?
Yeah, no, it's
Yes,
fine.
sir, we can see you.
Okay, so at least part of the problem is solved. Let me solve the next problem.
Absolutely fine.
This is a bigger problem than global warming, I think, the computer problem. So
Share your screen.
yeah, just a minute. I'm trying to share.
Uh,
Can you can you see my screen?
yeah, now perfect.
Yes, it's visible, sir.
Is the main screen? Can you see?
Yes, sir,
Yes,
we
yes,
can see.
yes.
Okay. So excellent.
Perfect.
So this
Hmm.
is this working. So I'm not that technically challenged yet. So just a minute. Your okay. Are you good? Are we good? Can you
Yeah.
hear me?
Yes, we
Yes,
can hear
yes,
you.
yes.
We can
Perfect.
see the presentation.
Okay. Yes. Excellent. So yeah, good evening, everyone. And it is
Good
Saturday
evening.
evening for you. So I'm really thankful that instead of really enjoying the weekend evening, you are out here listening to global warming. So yeah, so thank you very much for giving me the opportunity to discuss the role of carbon storage in achieving net zero. So I'm Raj Banerjee, as it was announced, and I'm an advisor in SLB. So SLB is previously it was known as Schlumberger. So recently we changed name to SLB. Our company is a global technology company. So we drive energy innovation. So initially it was all oil and gas, but we have also come to the realization that that we are transitioning to other forms of energy, which is non-fossil fuel. So and we are focusing a lot into it. So yeah, so today obviously it is not about oil and gas, even though all my previous work and expertise was in the oil and gas industry. But these days, I'm also looking at other new energy. So yeah, coming to that. So in this slide, it gives a view of SLB's initiatives in new energy. So oil and gas still remains the main business, but beyond oil and gas, we are very rapidly moving to this new energy, which includes carbon solution. So that is CCUS mainly, then hydrogen. So all the fuel cells and everything, also related comes over here. And then geothermal energy storage, and critical minerals, which goes into create many of the energy solutions. So this is what we have today, and rapidly evolving. So one of the important pillars in this equation is our effort into carbon solution. So, let us come back to the fundamentals. So what is the global primary energy consumption by source? So I've got this picture from our world in data, and it is generally consistent that almost 85% of global energy comes from fossil fuel. So we talk about alternate energy and all that. Even our focus is moving to alternate energy, but today, oil, coal, and gas is still the major source of energy. So fossil fuels account for over 75% of global greenhouse emissions, today. And also, so this is greenhouse gases, and if you consider CO2, it is 90%. Okay, and yet you see 84% of the global energy comes from fossil fuels. Now, you might think that, okay, we have made a lot of progress in alternate energy. Indeed, we have. So in absolute terms, there's a lot of change. But in relative terms, in 2000, it was, the fossil fuel contribution was 86%. So it's reduced only by 2%. So basically, even with so much effort, it is very difficult to displace oil, gas, and coal. And we have to indeed strive harder and do more to to move to sustainable energy sources. So we should not be complacent as to what we are doing today. Now, so what is wrong with fossil fuel? Okay, you might ask. I mean, it's easy to drill for oil. It is easy to get oil. It's all over the world. So actually the main issue, and you all know that, is carbon dioxide is produced when fossil fuels are burnt. So the CO2 in the atmosphere, when it comes, that traps heat, and this leads to global warming. And obviously, when the global warming happens, that leads to climate change. And if the climate keeps on changing, it'll be very difficult for us to live in this world, isn't it? Not only us, also, plants, trees, other animals, everything, the whole ecosystem is affected. So you look at the chart on the right, this is a record of atmospheric carbon dioxide level. And this is since when observation began in, I think in the late 1958, yeah. And you see the red chart over here. Over time, the CO2 in the atmosphere keeps on increasing. And this is a measurement, direct measurement, that is being done in Mauna Loa Observatory, which is in the island of Hawaii. So there are other observatories as well. This is one of the observatories, one of the oldest ones. And you see the CO2 level is rising. The up and down peaks and troughs which you see, that is the seasonal changes, due to vegetation growth in summer and in winter. In summer, there's more vegetation, so the CO2 level drops. In winter, the vegetation is less, so more CO2 gets to the atmosphere. But essentially, you can see from 1958 onwards, there's a huge increase in the temperature, in the CO2 level, which means there is a increase in temperature as well, in the global temperature. Let's go back to a more broader picture. So there's on the left, there's a picture there's a graph how the CO2 changes in the last 10,000 years. And it is both from direct measurements and also from, measurements from the air bubbles in ice cores. So how do you know? Nobody was there 10,000 years ago, how do you know what the CO2 level was? Well, this is from experiments. So what we do is we drill cores in the ice, and these cores means it's small samples you take out of the ice. And there is air, bubbles in the ice cores, and you can measure the CO2 in those ice cores. And deeper the ice, older you can say the ice is. So there's a correlation between depth, between amount of CO2 in the air sample, and you probably know all about all that. So essentially, the CO2 level in the last 10,000 years, as you see in this chart, that has been rising. And since the Industrial Revolution, so since the 18th century, you see the CO2 has considerably risen. You can see the graph over here. This is going, way past, what is normal. And in a few years, you'll see the CO2 will be so high that, global warming will create havoc with us. So there is a need, to control the CO2. That is why we want to move from fossil fuel to other things like, what we mentioned, like other sources of energy. So that brings us to the question, is that we have set a goal that, okay, by 2050, we will achieve net zero. So what is net zero? So one of the components of net zero is, it is a balance between the amount of greenhouse gases that is released, and, it's our effort amount of greenhouse gases or CO2 that is removed from the atmosphere. So if you release a lot of CO2, then you should be able to take the CO2 and you send it somewhere, So essentially that balance has to be zero. Now, that effort requires that you have, it is a multi-pronged approach. You definitely should be more energy efficient so that you use less energy to do a particular task. Focus on renewables, which is also a major thing. That is 35% each of these, and also sometimes fuel switching, like move from coal to gas, which is slightly better. So some effort over there. But also there is a considerable effort, say 15%, it is estimated that you should think about carbon capture, utilization and storage, CCUS. So virtually it is impossible to achieve net zero without significant CCUS effort. Okay, so so today in this talk, I'll talk about the storage part of it. So CCUS, you have carbon capture, utilization and storage. Sometimes we call CCS, where the utilization is missing, that is carbon capture and storage. So for me today, it is the storage part that we are going to talk about. Okay, so just a quick note that in SLB, we have been working on CCUS for many years, and so basically for 20 years now. And the reason why we have been working on CCUS for so many years is that many of the technologies that actually depend on effective CCUS project, those technologies are also oil and gas technologies, and I'll show you why it is. So when you say that you want to stop oil and gas production, this is fine. But many of the technologies which are there in oil and gas, we can effectively utilize for CCUS and for other renewable energies as well, in the new energy field. So over these 20 years, we have helped many sectors, not just oil and gas. We have helped decarbonize chemicals, cement, and so on. So so we offer a whole range of solutions. It's not just engineering solution, but also software solution, digital solution. And my job essentially is helping the software division of our company. So end of the day, I provide expertise in the domain science, but for software solutions. So let's look at this cartoon on this right. So we have the full picture, that is the capture, transport, and storage of CO2 in our case. So capture, I'm not going to cover today. It is, there are various methods of capturing, adsorption, chemical scoping, and looping, and so on. So then your membranes and, but that is not my expertise. But the first step in the CCS process is capture of carbon. So once you capture it, then you can transfer it. Then the next step is transport. So you can transport either as liquid or as gas through pipeline or through cylinders, to the place where CO2 can be permanently stored. So there are various transport mechanisms. Again, I'm not covering that today. It could be an interesting topic to talk about transfer of CO2 in pipelines, and we have software solutions for that. But that is a different story for some other time. But today we are talking about the permanent storage of CO2 underground. So another interesting thing, if you see on the left, is the International Energy Administration that estimates that the storage of carbon, it needs to grow from, currently we are only storing 40 metric tons of CO2 per year, okay, throughout the world globally. A lot of it is in the US. But from here we have to move to 5,000 metric ton per year by 2050. So 100 times. Okay, so which is a huge task. And it calls for effort not only in capture, but transport and also storage. So how and where and what technology is used to store this. Okay, so 2050 is not very far away. It will come very soon. So how we are going to achieve this, 100 times efficiency, I don't know, volume, and that remains to be seen. So yeah, we talked about storage. Now, so what is the mechanism of storing CO2? So essentially, if you see the picture on the right, on the left, let's look at the picture on the left. So what you're doing is after you capture and transport the CO2, then either liquid or gas, you are injecting it into the what we call formation, that is rock deep below the surface of the earth. And this could be, more than a mile deep, some 1,000 to 2,000 meters below the ground. So what you have, so you inject it in rocks. See, this rocks is just like a sponge. It has pore spaces. So you inject it over there, and and you're hoping, with all the studies we do, that will stay in place. It won't come out. So you look at the picture on the right. So this is what we call injection well. So there is a well, and this well could be, as I said, thousands of feet deep, going to the formation, to the rocks below. And this well is actually cased, means this well is surrounded by steel pipes, so that you are protecting the groundwater and so on, so the contamination of CO2 does not happen, and the well is in place, it doesn't collapse, and basically you can inject through pumps the CO2 in the underground reservoir, and that is the picture you see on the right. So you are using either pumps for liquid or compressors for gas to pump the CO2 underground. Now, what are these underground storage types? It's fine. It's not, you can't just inject it anywhere you like. So typically, our studies show that there are 5 types of underground storage. So the first is the saline formation, and all of them are not as popular. So let me at least tell the major ones. So saline formation is, you can see picture on the right, the CO2 stored in saline formation is way below the surface of the earth. And what you do over here is, these are saltwater aquifers. That means this is rock and it has salt water. And what we are doing is we are injecting the CO2 in this salt water. Okay, so, and I'll come more about, what happens when you inject CO2 in salt water, but that's what you are doing. And we are hoping that the CO2 will stay in place. So this is one method. And there are large number of CO2, formation storage, which is out there. And so there is no shortage of that. So we can do that. The other thing, type of aquifer, type of storage, other than saline aquifer, is, oil and gas reservoirs. So we produce oil from so many countries in the world, including India, and the oil comes out and it leaves a void. So you can utilize depleted oil and gas reservoir, and you can inject the CO2 in this oil and gas reservoir. So it is a two-way sword. When you inject CO2 in oil and gas reservoir, you can store the CO2 in this depleted reservoir. But there is another phenomena that is happening. This CO2 actually pushes the oil, so it acts as a enhanced oil recovery method. So in other words, CO2 is not just stored, but also it is used to actually push the oil. So the question is, so it has economic value. But the question is, when you produce oil, first of all, this fossil fuel is, there's global warming when you use oil. The other disadvantage is that when you're pushing CO2, using CO2 to push the oil, CO2 also comes out, so you're back to square one. So this is a case of mixed solution. You can store the CO2. Also, at the same time, you can gainfully use the CO2 to produce oil. And basically, you have to have a happy medium. Otherwise, so the solution is not black and white over here. So there are two ways. Okay, the third storage type is unminable coal seams, which is much shallower. So again, you have many coal seams which you cannot mine really. They are either very small or they're too deep and so on. So what you do is you inject CO2 and it basically gets absorbed in the coal seams, and it might somehow take out the methane, in a process called enhanced coal-based methane recovery. So methane comes out, and again it is a two-way process. Basically you have some methane, which causes global warming, but at the same time you're able to store the CO2. So yeah, so there are these three main ones, but there are also others like basalt formations and organic rich shales. So there are other types as well, but I just mentioned the three main ones. Okay, so what we have seen is we can capture the CO2, we can transport the CO2, and we can effectively store the CO2 by drilling wells or by using old wells into this aquifers or oil and gas reservoirs or coal seams. Okay, now what is the mechanism of trapping? So you're injecting CO2. So what happens? Does it really stay over there, or if it stays, where does it stay? So once you inject the CO2, so the next step is to ensure that the CO2 remains trapped underground permanently. Okay, so there are four main mechanisms, as you can see in the picture, in the cartoon. There are four main mechanisms that trap the injected CO2 in the subsurface. Okay, so one is structural trapping. So on the top left. So this is here the rock layers above and below the rock. They act as impermeable layers. Okay, and where you inject the CO2, that is porous, and that stores the CO2. So this is called structural trapping, and there are plenty of these all over the world. Then there is the residual trapping, where when you are injecting the CO2 gas, or CO2 liquid, it goes through the pore spaces in the rocks, and most of it, lot of it gets trapped. So essentially, it gets trapped in the pore spaces and it remains over there. That is called residual trapping. The third is solubility trapping, and this is when you are actually injecting in aquifers. So the gas the CO2 is soluble a little bit in water. If you have a huge water aquifer, so parts of it gets into solution in the water. So that is known as solubility trapping. Finally, you are over time, over a long time, this CO2 in water forms a weak acid, and this acid, so carbonic acid, reacts with the minerals in the underground storage, and that forms carbonates. Okay, so basically these carbonate solids, they remain underground and they're permanent. So these are the 4 different trapping mechanisms, and it is not one or the other. So all these 4, one or more of these 4 trapping mechanisms are happening in different types of storage reservoirs. So but it is important to realize this, because when you are and study this, because when you are actually doing the design and making sure that you do the right amount of storage and all that, so you have to actually understand this. So another question that comes in, and it's a bit technical, but yeah, let's see the basic overview, is that the PVT, or you can say the pressure and temperature behavior in this chart you see of the CO2 gas. So what happens is, you see the x-axis, you have the temperature, y-axis in this chart, you have the pressure. So depending on the temperature and pressure, you have different phases, either it is gas, liquid, or solid. So at the triple point, which is at 5 atmosphere pressure and minus 56 degrees centigrade, at that, below that pressure, you cannot have liquid CO2. So liquid CO2 has to exist at a higher pressure and higher temperature. So at atmospheric pressure and temperature, it is either gas or solid. That's why you have dry ice, what we call. Now, liquid is easy to transfer, obviously, because, the volume is low. So, if you transfer liquid through pipeline, it becomes pretty easy. If you have gas, then obviously you have to pressurize it. Now, on the top right, you see this supercritical fluid, low volume and low viscosity. This supercritical fluid happens in reservoir condition. Underground, you have supercritical fluid. So it is pretty good, it's a good thing that it's supercritical, it is easy to store. So that is what is going on in the right. So it is not a gaseous CO2, which you are used to thinking. It is a supercritical fluid that is there. Okay, so, so modeling and simulation. So our job, using computer software for modeling and simulation, so that can provide, among many things, key metrics in CO2 studies. Before you do the CO2 injection, these studies are conducted. So the main thing is capacity. We want to study amount of CO2 that can be safely stored. Safety is extremely important. Injectivity, rate at which CO2 can be injected. And containment, the ability to store CO2 safely and permanently. So if you want answers to these questions, you have to do some sort of modeling or simulation, as we call it. So the question comes in, what is a simulator? Why are you talking about simulation? Okay, so a simulator essentially is a mathematical model that is implemented as a software program. So my background is simulation. So not just CO2, it's also for producing oil. So traditionally, numerical reservoir simulators have been used for forecasting performance of oil and gas reservoirs. So all the reservoirs you have in Bombay High and others, you have huge simulation models, to forecast the performance. But what we have done is we have extended that reservoir simulator and we can now use it for CO2 storage as well. There are a few changes to the functionality which we have effectively done. Okay, so it is not, so this numerical reservoir simulator is a flow simulator. It actually simulates or models flow of flow of liquids and gases in the reservoir. A solid doesn't move, it stays in place. Liquid and gases in the reservoir. So yeah, so this is the numerical simulator, but there are other types of simulator we have. The other one is geomechanical simulator to study the geomechanic properties, and pipe flow simulator to study the flow of fluids through the pipes, through wells. So all these different simulators are extremely important, and we have to work with them. So there are some key things which are important for modeling of CO2, and which we have, studied this and put them in our simulator. So one is that, this CO2, it requires complex multi-phase physical and chemical behavior, that needs to be studied. So basically the equations we have, they are, they honor the phase behavior, which I showed earlier, whether it is liquid or whether it's supercritical, whether it is gas. So this multi-phase behavior, it can model. And also what happens in oil and gas, we were typically focusing on 30, 40 years of simulation. That means, the model would be able to predict what happens in 30, 40 years time, because, or even 50, 100 years. But when you are simulating CO2, you want to actually simulate and see what will happen in 1,000 years, 10,000 years, so on. So longer than usual simulation period, in thousands of years, that is important in our software. The other thing is, this CO2 storage has a lot of elements of different domains, economics, flow assurance, geochemistry, geomechanics. So all these are important in considerations, and that needs to be included in our simulator. Okay, so yeah, and our simulators do support that, and the studies we do takes into consideration all this. Okay, so one important thing when you are storing CO2 underground is the effect of geomechanics, because when you are increasing the pressure by injecting CO2 underground, you have the risk of actually fracking the reservoir. So the cap rock, or the rock that actually seals the CO2, that can break. So basically how much you can pressurize, that needs to be studied through simulation. So this is what we call cap rock integrity. Then underground reservoirs have faults. Fault means, they have breaks in the rock. So are these faults actually sealing or non-sealing? It is important. Otherwise, CO2 will escape through these faults up to the surface. So that is a big issue. Then you have the reservoir properties, the permeability means the ability of the gas to flow through the rocks and get in place. That, and the porosity, the capacity of the reservoir to store the CO2, that changes with time. So that is why we are telling reservoir property evolution. And this is again due to geomechanics, due to changes in stress and strain in the reservoir. So containment, how much of the container you have underground. And also, you could have induced seismicity, earthquakes, okay, which again affects the storage. So all these things has to be studied. So what we have done is we have a new geomechanical simulator, and we have a flow simulator, and we couple both of them. So these can be coupled, and when we are doing the study, we have a two-way coupling, and we do the study with both the simulators. Okay, the other important consideration is the well consideration. So you have studied the reservoir, you know how much you're going to store, how much you're going to inject, all these things you have determined. But the question is, will your well, as I described, it is cased with iron, okay, cased with steel. So your steel well, which is 1,000 or 2,000 meters deep, will it withstand the flow? And you're pumping in CO2. So the wellbore integrity, then the CO2 is at a different temperature than your underground reservoir. So this thermal effect that induces formation damage. That means your rock around the well can become damaged. So if it gets blocked, then it is blocked. You cannot inject anything. So all these things needs to be studied. And then finally, and very important is the mechanical failure. If your well fails, then and collapses, then you are in serious trouble, because neither you can inject anything, whatever is underground that might come out through the well. So huge, safety hazard. And then if you're, the mechanical failure happens, then you could even contaminate drinking water. So the stakes are high. So essentially, the wellbore effect studies are extremely important, in addition to the study of the rocks or the reservoir storage that goes on. Okay, so these takes time, and these sort of things, a lot of science involved, a lot of economics involved, because everything costs money. And obviously, when you're injecting, so you get some tax benefit, but other than that, it takes a lot of money to do this. So for us, how much time do I have? Okay, quickly. So this is the integrated workflow for storage evaluation. On the right, we already described in the picture that you worry about storage capacity, storage mechanism, injection planning, plume modeling. Plume is the CO2 that is underground, that is called the plume, and it moves and it changes. So modeling that, through simulator, containment, integrity. And also when you are actually injecting the CO2, you monitor it. It's not that you inject and forget. So you have to monitor to see that everything is in place. So there is MMV, there's a verification, monitoring, measurement, and verification, that the CO2 is not going anywhere else. It is staying in place. So all these studies you see on the right. In the middle, we are talking about the simulators, which I already described. But what is important is, on the left is the data. Simulators cannot run by itself. It is like a video game, though. It runs, but it needs data. So you have to feed in measurements you make underground. So log basically is a response of the nuclear or electrical properties underground in the bottom of the well. So through these responses, you can get an idea of the properties in the well, in the reservoir. And also you can have seismic measurements. It is like ultrasound. So you do some seismic shots, and then it reflects from the reservoir underground. And through that reflection, you can analyze them, and you can get an idea of what with the shape of the storage which is underground. It is just like ultrasound in human body. Then you have core data. Means when you are drilling the wells, you take out samples, of rock, and you can analyze them, and you can, again, that data goes into the reservoir simulator. And also you have the drilling data, of course. So all this data is required by your simulator. So it cannot exist in vacuum. And again, this data is hard to get, because it costs a lot of money, and often engineers have to make the decision as to whether to do this data acquisition and do a proper study, or make assumptions. So it is again, here also there's a fight between economics and what is the proper way to study. So often we have to balance between what is good to know and what is need to know. So that is always there. And what I'm trying to say is that a lot of data acquisition methods need to be used, and the accuracy of your model would depend not just on the simulator, but also on the data which you feed it. Okay, so overall, this is the picture of storage and the studies we have to do, the high-tech studies we have to do to ensure that what we are storing makes sense, it stays in place, and so on. So I'll give you one case study. This is, it was a couple of months back. I was personally involved in this study. So it is a joint study between University of Houston, which is a university in Houston, as you know, that the name suggests that. So University of Houston, the students, and so the work was done by the students there. Students and a couple of professors were involved as well. Capture Point is a company nearby. They are in the business of carbon storage. So those guys were there. They gave us the data and everything. And SLB, that means Schlumberger, that myself and few of my colleagues were involved. So we were mainly supplying the software and helping people with the software and with the technology, science, and so on. So we created the flow model, fluid flow model. We did some forecasting and so on. But it is interesting about this project is that it is not just carbon storage. So what Capture Point had was a depleted oil and gas reservoir. So this reservoir, they were producing oil since 1952. So they produced oil for some time. And then when the pressures became very low, nothing was coming out. So they started flooding it with water. So they started injecting water, and water pushed out some of the things, some of the oil, and so far so good. Then they realized even water is not good enough. So they went in what I described was the enhanced oil recovery. So they were injecting CO2. So fine, they were injecting CO2. It was pushing the oil. Both oil and CO2 was coming out. And then the question come in, all this focus on storage, on net zero and all that. Then Capture Point said, hey, why don't we store the CO2 rather than use it to push the oil? What would happen? How much we can store? And obviously for Capture Point, it was also a question. If you store CO2, you get tax credits. So let us take the tax credit. Everything is economics in here. So because there aren't much oil anywhere left, so nothing to lose as well. We can store a lot of the CO2. There are some power plants and some cement plants where they can capture the CO2 and store it. So it was a very interesting study, a couple of months. And, so this is a model we made. And you can see on the right, how the plume is moving in the reservoir. Okay, there is another case study. So earlier, the last slide, it was depleted oil reservoir. Here, I didn't do this. A colleague of mine did it in Australia. So here we are injecting CO2, and this CO2 is moving in the reservoir. As you can see, this is the animation. This is the simulator. It is moving through the reservoir. Okay, you can see the simulation model, and the CO2 is getting dissolved in water. You see on the side, you can see the water-bearing layers, and it is forming an acid. It's moving and getting dissolved in the water over here. So this is a typical case in Australia of it is the coast of Australia offshore, and this is the case where CO2 is getting stored in aquifer. So there are two cases which we have shown. So yeah, I think so I can go on about this and particularly the science of it, but this is to just give you an overview on Friday evening. Not the best of times though for you. So what we are telling is that for us in SLB, this is very exciting times, and we have integrated projects where our experience comes into play. So we have integrated services and technologies for selection, planning, construction, operation, and monitoring of sites. So it's much more than what I described. There are various domains involved. So we do site identification and appraisals drilling and well construction. So all these things, we have experts doing that, and typically the studies which we do are multidisciplinary. So it involves geology, geochemistry, not only reservoir engineering, dynamic flow, geomechanics, and so on. And end of the day, the thing that is important is uncertainty and risk analysis. So all the engineers or geoscientists, the primary thing in their mind is, what is the risk? How uncertain is our result? So yes. So we have over 50 CO2 storage projects around the world in recent years, and we are looking forward to more. We want a net zero sustainable world. Thank you. I think you have some. Do we still have some time? We can leave for questions, if any.
Thank you so much, sir. It was indeed an insightful session from your side. Now I would like to pick up some questions for you, if you can kindly answer them. So the first question goes like, how the company ensures that the structural layer below is capable of storing the gas, how the permeability is determined, how the capacity modeling is done, and there's another part, is it geological data that we need for forecasting?
Yeah, these are very good questions. I could go for a 5-day course on this, So there are a few things that happen. Subsurface, you need geological data, obviously, because we are talking about subsurface. So you need permeability, porosity, and the geomechanical properties and so on. And all these properties are, as I mentioned, used by the reservoir simulator to do the forecasting. So you just have geological data, nothing will happen. You have to actually model the flow. And that is where reservoir engineering or petroleum engineering comes in. So I'm a petroleum engineer. So I take this data which the geologists give us and do the analysis. Now coming to permeability, somebody, I think you mentioned, what about permeability? Permeability is something which we do some testing. So that is called well testing, where you measure the pressure response underground. And then once you have the pressure response, you can use the rate data. And there are, again, computations which allow you to calculate the permeability of the reservoir. Either you do that, or you have core samples. You have samples of rock from underground, and you do lab experiments to get idea of the permeability and porosity. So yeah, but it is a very detailed process, which would take some time to explain. But this, in short, is, I guess I answered some of your questions.
So there was another part regarding capacity modeling, if you can mention.
Yeah. So can you repeat that? Capacity modeling, yeah. So the simulator tells you the capacity model. So basically, when you are simulating it, then it will tell you in each. So what happens in a simulator? You are the mathematical model. You are breaking it down into grids. So what happens in, you can calculate, the simulator calculates how much of pore space is there and how much of CO2 is there in the space. So you get from the simulator the storage capacity for each of the grid blocks, and then if you have the bounding volume around the CO2 due to impermeable layers or whatever, you get to know what is the storage capacity through the simulator. Yeah.
Thank you so much, sir. The next question is due to global. The next question is why we are not using BESS, FESS, or CAES in smart microgrid or grid.
Using for what?
So why we are not using BESS, FESS, or CAES in smart microgrid or normally in a grid?
I don't know why we are not using.
No problem, sir.
Yeah.
So
I can talk about our, yeah. Okay, go ahead. Yes.
So the next question is regarding the CO2 injection. So can we use CO2 injection like to store CO2 as a source of energy?
Well, CO2, you're storing the CO2. Now, how would you so one of the things is that when you are injecting CO2 in oil reservoir, then you can use the CO2 push the oil to the producing well. So basically, it gives kinetic energy to the oil, and you produce the oil. So there is a source of energy. But the idea of storing CO2 essentially is to, store it permanently. That is the main part. Everything else is noise. You want to store it permanently. If you want to use the CO2 for anything else, then you can do that before storing. But if you store CO2, part of the CO2 you can produce. You open it's a injection well, you convert it to a production well, you can produce it.
So in the sense, we can store that in the like CO2 in the CO2 injection.
Yeah, in the reservoir, you store it. And so typically the idea is to store it permanently. But for any reason, if you want to take it out, it's like a bank, isn't it? You open up the well and it can produce. It can't produce all the CO2, but it'll produce some of it.
Okay, sir.
But the main idea is to store it. The design we do is to store CO2 permanently. Okay, coming a little bit about, I think there is a little bit of interest on the modeling part. On our model is a numerical simulation model. It is a finite difference model, which means, so it is not a finite element model, it's a finite difference model. And the reason we do it, because finite difference, the equations are particularly amenable when you have multiple phases, when you have, gaseous and liquid phase, and then there is what we call compositional equation, even if there is oil and other components, when the components change, so we have what we call compositional simulation, which is kind of very complex, but finite difference simulators work very well in this sort of situation.
Thank you so much, sir. So the next question is that we know that tectonic plates, it causes a lot of movement. So will there be any complication regarding the CO2 injection? And what do we do regarding such complications?
Yeah, this is a risk. We try to, through geomechanical simulation, which we see the effect of tectonics also. So you cannot completely predict what is going to happen, but we do study the effect of seismicity in our models. Yeah. But again, it depends on the data you have. So if there's a huge earthquake, so predicting earthquake is something, and then if the earthquake is there, what happens to the CO2 storage reservoir is something else which we need to compute. Given there is the risk of earthquake is one thing, and given there is an earthquake, what happens to the storage, that is something which we calculate. But we cannot, our simulator does not predict if the earthquake will happen or not.
Thank you so much for your answer, sir. The next question is, if CO2 is dissolved in the water in underground, then we may have like potential issues regarding the drinking water. So what is the solution regarding?
Oh, this is an excellent question. So when you are injecting CO2, it is deep in the reservoir. It's way below drinking water. So this is, miles deep. And when you are drilling the well for that, which I showed, I think, in one of the slides, you have a casing. So you have a tubing that is, the well is cased with steel. So we make sure that the CO2 does not escape to the drinking water reservoir. A drinking water reservoir is very shallow. Whereas when we are injecting, it's way, way deeper. And we make sure that there's a barrier. The well integrity is maintained and there is a barrier against drinking water. And it is not just for CO2, even for oil and gas production, all these oil wells you have, in Assam and all that, there is always a fear that if your casing fails, you would contaminate the drinking water. So we have to be very, very careful about this well integrity, what we call it. But do accidents happen? Yeah, they do happen.
Thank you so much for your answer. So the next question is from my side. So we know that soil sequestration is one of the methods for carbon storage. So considering the fact that land is considered as a luxury in today's time, so how do we consider soil sequestration as effective? Like, we need a proper land in order to store the carbon, and we know that land is not available as far as India is concerned, like it is overpopulated in a sense. So
yeah, exactly. That is why you are actually supporting my statement. That is why you should inject deep underground, when it's not coming into anybody's way. So you drill deep, 1,000 meters or 2,000 meters. It doesn't disturb any of the people out there, and you store your CO2. And if you look at depleted reservoir, and you have a lot of aquifers, by the way, both offshore and onshore in India. And if you don't want to, these aquifers are saline aquifers. They're not drinking water aquifers. So you can do that in India. And in India also, you can inject in depleted oil reservoirs. You have so many depleted oil reservoirs, sitting there in Assam and in Gujarat. You could go and do that very easily.
thank you so much, sir. Now I would like to request Piyali ma'am to kindly give the vote of thanks.
Yes. Yeah, Suryankshi. Thank you, Suryankshi. So thank you, sir. Thank you very much for this wonderful speech. So within the Saturday evening, it's our evening, but it's your Saturday morning. So we are we are glad that you started your Saturday morning with us. So at least your weekend, you spend your weekend timing with us. So and you agreed to spend this time with us for our students and our AE participants. So we have more than 60. It's about 60 participants today. We have for this lecture. So I would like to thank Dr. Banerjee for accepting our invitation from our AE Kolkata chapter and giving their wonderful session. So students have, I found the students have many queries with your lecture. So so in future, if you visit Kolkata, so we would like to invite you for a offline session interact with our student,
Yeah, it would be nice to have a coffee sessions, for question answer, any type, so that would do. Not just CO2, but, oil and gas or whatever, AI, machine learning, whatever you want.
Thank you, sir. Thank you. So so I would like to, this is a formally, I would like to thank all the participants who are present today from our institute, from our SWBM, and also from different colleges around the Kolkata and other cities. Also AE participants, like AE members are also present, few members. So I would like to thank all of them for presenting today to present today in this session. So my thanks also goes to our team members, our core team members, our directors, Sri Dipankar Dasgupta, then Vice President Dr. K.M. Agarwal, Dr. B.K. Chaudhary, and Secretary Dr. Arindam Datta, and Joint Secretary Dr. Sharvani Mitra. Along with this is our student team members, AE Kolkata chapter student chapter members like Shreyanshi, Reek, Avanisha, then Hemanta, and all others, many students. So actually they are the main co-host of this sessions that we conduct every month, and we invite different speakers from around the world. So that's it. So, and one thing I want to mention here, that after today, so I think our one of our newsletter, and on this newsletter, this energy window, a newsletter from our AE Kolkata chapter, which is going to be available in our website. It's freely available. So September issue is going to be available from today itself. So those who want to avail those newsletter, please go to our website and avail this one. So thank you, sir. And thank you very much for, it's already 5 minutes. We have taken your time extra, that it's already 8:05. So thank you so much. And we would like to hear from you in future also in our this kind of talk. And also we have our annual AE meetings and annual conference we conduct every year from say in the December and January. So if we would like to invite you for the session also. If,
Thank you. Yes, I'm a member of AE, so
yeah,
it'll be good to
that's
see
it.
it.
Yeah. Thank you. So hope you joined the different sessions with the AE USA chapter. So share with us their experience with our students, and we will meet you there. So thank you so much. Thank you.
Thank you. Bye-bye.
Thank you.